Okay. So, welcome everyone. This is our fourth deep learning seminar of the year. Today, we're honored to have Dr. Haotian Jiang. He is a postdoc at CNRS, Create, and did his PhD in mathematics at NUS. Today, he will be talking about approximation rate of the transformer architecture for sequence modeling. So, after you, Dr. Jiang.
Okay, thank you for the invitation to the seminar. And today I will talk about the approximation rates for the sequence modeling architectures. Okay, so let's start. Okay, let me see. Okay, so what is sequence modeling? So sequence modeling is basically a class of machine learning problem where the inputs and outputs are both sequences. So let's see some example here. So in machine translations, both the input and output sequences can be considered as a sequence. The sentences can be considered as sequences. And also for some mathematical applications, if you look at the control systems, we can consider a control signal as a sequence input and the corresponding response as an sequence output. These are all sequential structures. And recently, there are also some other applications that does not have very obvious sequential structure, but can also be solved using sequence modeling techniques. For example, the image classifications. Here we cut the image into image patches, and we regard the image patches as a sequence input. So in order to analyze the sequence modeling problem mathematically, we need some kind of abstract formulation. And we use the following formulation, which should be general enough. So the input space here, the input here is defined as a function from time index t to some vector, to some d-dimensional vector. So here the I denotes the index side. And the output, we consider scalar valued sequences. And the target, we look at the target here. So ht is a functional. So the meaning of the definition here is that the output at time t potentially depends on the entire sequence x. So the output at each individual time step, we can write it as a functional. And to consider the output at all time step, to consider the output at all the time step yt, we write it as a sequence of functionals. So this is basically our formulation of the sequence modeling problem. And let's look at an example, a simple example here. So this is a convolution of an input x with a Gaussian kernel. So basically, this is a sequence-to-sequence relationship. And the meaning of this relationship is that we are doing some smoothing operation on the input sequence. Okay, so our goal here is to learn a target h. So we write the boldface h as our target using some model h hat from some hypothesis space. And in fact, in sequence modeling applications, there are different architectures. And basically, I listed here is basically three main families of the different architectures. So first is the recurrent ones. The recurrent architecture basically consists of a hidden unit, a recurrent hidden unit here. And it is updated recurrently based on the inputs at each time step. And for example, this is first developed from the recurrent neural networks. And recently, there are also development in the state space models, the SSMs, for example, the S4 model and others. And mostly the recurrent architectures are applied for some time series applications, for example, the forecasting, weather forecasting, and the time series related stuff. And we also have the convolutional architectures. For example, the temporal convolution networks. So the convolutional architectures basically use a 1D convolution with the input. And we also have the wavenet, the convolution architectures are mostly applied for some very long sequence processing, for example, some audio generations, for example, the wavenet. And finally, we have the attention-based architectures, which is a transformer. And I think it has become the default choice for most of the for most of the language processing problems. And empirically, depending on the tasks, there is no single architecture that is always good. So on some of the applications, we may use recurrent ones. On some, we may use convolution ones. And on some other applications, we may use transformer one. We use the transformers. So we want to ask a question, what are their fundamental differences? So given architecture, can we decide the type of targets that it is good at? And we are going to try to answer these questions through approximation theory. And so now let me give a brief introduction of approximation theory. So there are two main parts. There are two main things we are considering in approximation theory, which first is a target space. So the target space is a set of functions that we aim to approximate. And we also have the hypothesis space. It's a set that consists of all the possible models we use for the approximation. So basically, we can say all the models is from the hypothesis space, and the target space is the target we want to learn. And the famous theorems, the most famous theorems in the approximation theory, I think, is the universal approximation properties. So for UAP, we can say that a hypothesis space H has UAP in a target space C if for any target from the target space, there exists some H from the hypothesis space such that they are close enough. And actually, all the architectures I just talked, for example, the RN, the SSM, the transformers, they all have UAP in some appropriate target space. So we want to consider if both architecture have UAP, how can we distinguish them? They can approximate all the continuous functions, but how do we know whether what's the difference? So in order to answer this question, we consider the approximation rate. So here we consider approximation of continuous functions using polynomials as an example. So here the target space we considered is a continuous functions defined on the interval 0 to 1. And the hypothesis space we consider here is all the polynomials. So I'm here, we call it approximation budget. And here is basically the order of the polynomial, which is the number of parameters here. Okay, so the Jackson theorem states that given any function, given any target, which is alpha times continuously differentiable from the target space, then the best possible polynomial approximation error satisfies this equation here. So on the left-hand side is the best approximation error. On the right-hand side is the upper bound. Here C is here CH, we call it a complex measure of the target H. So it's basically the subnorm of the continuous function, of the differentiable function here. So what we can get from this theorem is that smaller complexity measures. So if this complexity measure is small, then we have lower error bound. And if the target is smooth, which means that if a target have a larger alpha, then this error decay rate, then it has a faster decay rate, which means that when we increase the order of the polynomial, the error will decay faster. And so we want to, so this theorem, basically the approximation rate theorem tells us that polynomials are good at smooth targets. And we want to develop similar result to the sequence modeling architectures because this can tell us that what kind of targets the architectures are good at. And here we also note that we are considering a subset, which is differentiable functions. So the reason is that for all the continuous functions, we cannot have an approximation rate. We must have some regular subspace in order to develop the approximation rate. Okay. So here, let me review some existing results for RNNs. So let's consider a linear continuous RNN which has the following formulation here. So H here is the hidden unit, is a hidden recurrent unit. and X is the input. So the target space we considered here is all the causal time homogeneous and continuous target, continuous functionals. And it can be shown that for all the operators, for all the sequence of functionals satisfying these conditions, we can have the following, we can have this representation here. So this means that all the functionals satisfying these conditions have a unique representation using this function here. And we call it a memory function. So basically this function rho characterizes the memory of this relationship. And based on the previous result, we have the following approximation rate for RNs. So basically on the left-hand side is the best approximation error, and the right-hand side is the error bound. And here we have two complexity measures here. So the first, we have alpha, which measures the smoothness of this memory function rho. And we have the C1, which measures the decay rate of rho. So basically here we assume that this quantity goes to 0 as s goes to infinity. So this shows that when C1 is small, the rho here will be decaying faster. And C2 here measures the magnitude of the derivatives here. So this is a bit abstract here, and I will give some example here. So on the left-hand side is a target with low complexity measure, which is a convolution with exponential decaying kernel. So this memory function here is actually smooth and exponentially decays fast. So RN can learn these kind of targets very efficiently. However, if we look at some example of high complexity measure, let's consider a convolution with some impulse kernel. So this relationship describes that the output sequence is a shift of the input sequence by some time steps. So the memory function for this one, you can see it's a spike at 10. It's a spike at time step, at the time step 10. So basically this target is not smooth. So and the RN is actually very hard to learn this kind of target. And this one is, we can also say that this has a long-term dependency because the output at time t depends on 10 time steps further from it. And RN is hard to learn this kind of target. Okay, so we know that Rn depends on smoothness and the decay of the memory function. How about other architectures? Okay, now let's look at we now are going to look at the transformer architecture. So transformer is an architecture based on the attention mechanism here. So attention is the most important part of the transformer. And transformer has become the building block of many famous large language models nowadays. And we will try to understand how it's different from RN, CNN, and other architectures from an approximation perspective. Okay, since attention is the most important part, let's first look at it mathematically. So given input, this formula describes the attention here. So given input sequence, attention is basically a weighted sum of all the inputs, and the weight of the weighted sum is calculated using the attention. The attention weight is the pairwise inner product of the core and the key vector here. So let's see the figure here is suppose we are giving an input sequence X. First, we will apply some mappings to transform each of the input tokens to some vectors, which is a QKV vector. And the attention matrix here is calculated by the pairwise inner product of the QK vector. And we apply a softmax here to each row of the attention matrix to make it sum to 1. And then we time it with the value vector to form up the weighted sum. So this is basically the mathematical formulation of attention. Next, let's look at the transformers architectures we considered in our papers here. So the main components of a transformer is a stack of attention and feed-forward neural networks. So the hypothesis space we considered in our setting, we consider the most simplest one, which is a one-layer transformer with one attention height. So this is basically the attention. Sorry. So this is basically the attention with the feed-forward neural networks added to it. So the input has a pointwise feed-forward mapping, and the output and the entire output also has a nonlinear feed-forward output. So this is it can be considered as the most simplest transformer setting. And HT here actually maps the tau here. Sorry, the tau here is the length of the sequence. So because transformer is applied on some finite length sequence, so we assume the finite length is written as tau. So the input sequence can be considered as tau by D matrices. So this means that each input token is D-dimensional, and we have tau input. We have tau input tokens, and HT is a mapping from this one to a scalar sequence. And the attention weight matrices is written as the WQ, WK, and the WV here. And these two Fs are the feed-forward neural networks. And the approximation budget here is the hidden dimension of the hidden size of the transformer, the MH, which is the attention matrix size. And also the MFF here represents the number of parameters in the feed-forward part. So our goal here is to investigate the density and the approximation rate of this hypothesis space in some target space. So for the target space, do we consider all the continuous functions from the domain to the range of the transformer? And the answer is no, because transformers are permutation equivariant, which means that for any permutation P, if we permute the input, the output will be permuted in the same manner. So this basically says that transformer can only approximate target that have the permutation equivariant property. And in general, the most simplest solution is to add a position encoding. And here we consider the absolute position encoding, which we add which says that there is a vector. So this vector is time dependent, added to each time token of the input sequence. And equivalently, we can consider a different definition of the input space, because we can see that this operation is totally on the input space. So here we look at an equivalent definition of the absolute position encoding by using a different input space. So we assume each time the domain of each time token are from pairwise disjoint compact sites. And we define the input space. We define the input space on these disjoint sites. So this means that all the tokens at different time steps are not overlapping. And this input space is not geometrically symmetric. So this means that we do not have the permutation equivariant problem on this input space. So we can define the target space as all the continuous function from this input space X to all the scalar sequences. Okay, so indeed the hypothesis space is actually dense in it. Let's see some density result of the transformers. So in our paper, we proved that for fixed depths, because we are considered a one-layer transformer, and infinite width transformer are dense in this target space. So this we can prove this one. Yeah, we have proved this one in our paper, and some previous density result of transformer says that infinite depth and finite width transformer are also dense in this target space. And some further result also says that transformer with sparse attention. So we consider the attention we consider are general attentions. And in this work, it shows that if the tension matrix follows certain sparse patterns, then they also dense in certain special target spaces. Okay, so basically we have the density result, which can be easily proven for the transformers. And like the continuously differentiable functions approximated by polynomial, we want to investigate the approximation rate to have a better understanding of its approximation power of the transformer. And recall that for the approximation of polynomial in continuous functions, we need to consider some regular subspace. For example, the continuously differentiable functions. This is same for the transformers. We need to consider some regular subspace of the target space, because for all the continuous functions, we cannot have a rate on it. So in order to consider the regularity of the target space, let's first look at a general transformer form. So why we say this is a general, because we basically copy the linear transformer form here, but we're considering the pointwise functions here, the pointwise mapping here, to be some general continuous functions. So the big F and small f here are some general continuous functions. And the pairwise interactions here, the pairwise interaction, we also write it as a general bivariate function. So we consider we say this is a general transformer form. And indeed, this form has some special properties. We have the following representation theorem of the target space using this form. So let's say for any target from the target space, so H here is any continuous target, there exists some continuous functions, big F, small f, and rho, with the dimension satisfying this quantity, such that the target can be exactly written into this form. So this means that we have a representation of all the continuous functions by using these three functions, big F, small f, and rho. So this is so that we can propose regularities on these three functions here. And by proposing the regularities on these three functions, we can have a regular subspace for us to consider the approximation rate. And indeed, the approximation of these two pointwise functions are using the feed-forward part. And the approximation of this pairwise interaction function rho here is using the attention part. So since this one, the approximation using attention is the most interesting one, let's first look at it. So the attention matrix is written into this form, and we can rewrite it into the following. We can rewrite it in the following form, and we can see that the attention mechanism is basically a product of the input and output mappings separately. And so for the target function rho here, we can also consider its POD decomposition. So this is actually the spectral decomposition here we use to consider the bivariate function here is the POD decomposition. So the rho in the target representation can be decomposed into this form, where the phi here is where the phi and psi here are the eigenfunctions of the rho, and the sigma here is the singular values. So this can be basically considered as an infinite dimensional singular value decomposition for functions. So now the approximation here is using, we want to use a tension rho height here to approximate the target rho here. So the POD decomposition tells us that this follows low rank approximation. And the approximation error is completely determined by the singular values here. So we can define the complex measure for rho in the following form. So the meaning here is that we assume the singular values have certain decaying patterns. Here is a decaying, we are assuming the singular values are decay with the alpha measures its decay rate. So the approximation error is completely determined by the singular values. And this complex measure can be used to quantify the approximation rate for the pairwise interaction part here. And for the regularities regularities of the feed-forward part, this is actually the approximating of continuous functions with feed-forward neural networks. And here we do not assume a specific architecture for the feed-forward part, because these approximation results have been developed before, and the rate all satisfying this form. So for example, binary sigmoid neural networks have beta equals to 0.5. And because we do not assume a specific architecture in the feed-forward neural networks, we can keep this part in general, which means that we are assuming that the feed-forward part already have some certain approximation rate based on based on existing result. So this complex measure here measures how the continuous function big F or small f can be easily approximated by a feed-forward neural network, and the beta here is the decay rate. So now we define the complex measures for all the pointwise functions denoted at C2. So this has three parts. We will need to approximate the pointwise function f, big F, small f. Also, we also write rho here because let's go back to this side here, because we see that we need to approximate the eigenfunctions of rho using the feed-forward function, using some feed-forward neural networks here. So this complex measure C2 measures basically contains all the pointwise functions we need to approximate using feed-forward ones. Okay. Now we can look at the approximation properties of the transformers. So the regular subspace we are considering here is all the continuous functions from this target space such that it has a finite complexity measure of C1 and C2. So by considering this regular subspace, we have the following Jackson type approximation rate theorem for the transformers. So let's consider a sequence with length tau, and for all the target H from this regular subspace, the approximation rate satisfies this equation here. So let's take a look at the approximation rate here. So basically, it contains two parts. One is considering the C1, and one is considering the C2. So the C2 complexity measure represents the complexity associated with approximating big F, small f, and rho using feed-forward components. So this one basically if we assume the MFF, which is the parameters in the feed-forward part of the transformer, if we assume this one can go to infinity, then this term will go to 0. So we can just assume we have a large enough feed-forward neural network in the transformer. But we can see that even though this term goes to 0, we still have another term. here. So this means that by only increasing the size of the feed-forward network is not enough. We still have this arrow related with the pairwise interaction here. So let's take a look at this arrow bound here. So let's take a look at this term here. So C1, let's recall, is determined by the singular values or the spectrum of the target representation row. And we assume its singular values is have this decaying pattern. And we see that the decay rate of this arrow bound is related to the singular value. It's determined by the singular value decay rate of the target. And when we increase MH, which is the size of the attention, this term can go to 0. And this shows that transformers are good at approximating the target such that it has a low rank pairwise interaction term. It has a low rank pairwise interaction. And let's look at some experiments to show what does it mean by the low rank here. So in order to estimate the rank of a real data set here, we consider the vision transformer on CIFAR10 data set. Because we cannot directly estimate the singular value of a data set, of a target relationship, we estimated it through a sequence of models. So here we have a sequence of series of transformers where we have the increasing size of its attention. And we want to see that whether the singular value decaying pattern converges to some fixed patterns. And we can see that, so for different MH, we are increasing the attention size from 1 to 64. And we can see that on this plot, we plot all the singular values of the attention matrix. And we can see that when we increase the size of the model, the singular value decaying pattern converges. So this means that we can use this one as an estimate of the target of the single value pattern of the target. And we can see that it actually has a low rank pattern here, because we are only plotting the first few singular values, and it is already converges to 0 very fast. So that we can see that there exist low rank structures in practical data sets. And we also plot the arrow, the approximation, the training arrow here against the attention size. So we can also observe that the arrow here also follows a power law decay. This basically illustrate the low rank pattern in some real data sets here. And for target with low rank patterns, the transformer can indeed learn it efficiently. And let's look at some implications from the approximation result. So recall that we want to answer the question, what is the difference of transformer with other architectures? And here we are going to answer this question here. So the first implication here is that temporal ordering is not important for transformers. So what does it mean for temporal ordering? Let's see this proposition here. So suppose we consider some target. We consider some target H from the target space, and let P be a fixed permutation. So suppose delta H is defined by this equation. So this means that the delta H has the same output with H, but the input is permuted. So basically, we are considering an altered target where the input is permuted, but the output is fixed. So this is we are considering the temporal ordering in the relationship, because after we permute the ordering of the input, the internal temporal relationship will be completely changed. But for the target space we considered here, we still have the outer target is still in this target space, and most importantly, we have that the complex measure of this outer target is same with the original target. So this means that the approximation power of the transformer is same on these two targets. So what does it mean is that let's take a look at this simple experiment. So if we permute the input data set and keep the output unchanged, and we train the transformer on it. So on the first row is the result for the original data set, and the second row is the result for altered data set. We notice that the performance of the transformer is nearly identical for these two targets. So what does it mean is that the ordering of the input sequence is not affecting the performance of the transformer. So transformer is actually not seeing the temporal ordering of the input sequence. So this actually can be both a good thing and a bad thing for transformer, because it totally depends on the target. If the target does not include any temporal ordering information, for example, the image hashes in the image classification problem, then transformer can learn it really good. But for some applications where the temporal ordering is important, for example, the time series forecasting, transformer is not good at such task, because this task has strong temporal ordering relationships, but the transformer are not taking them into considerations. Okay, nice. Let's look at another operations, which we call temporal mixing. So temporal mixing will affect transformers. So what does it mean by temporal mixing? So here, let's suppose some target H is defined by this equation, where the where the theta here is some convolution is some 1D convolution filter. So this equation means that we are considering the output. They have the same output, but the input is changed using a convolution filter. So in other words, we are assuming that there are some kind of mixing of there are some kind of mix of the input tokens through the time direction. And we have the following proposition. So there exists a convolution filter theta such that for the altered target, we have the complex measure of this target is greater than the original one. So this means that the approximation power of the transformer will become bad on this altered, will become worse on this altered target. Oh, sorry. So this means, but here I want to mention that it is generally hard to determine how exactly a complex measure changes if we give an arbitrary convolution filter here. But this kind of shows us that if we can applying some convolution to the input before feeding it into the transformer, this may improve the transformer performance. Okay, let's make some comparisons with the irons. So we are again considering experiments on the linear functional targets. And here I want to mention that the temporal ordering is actually not affecting the performance of the transformers. So if we look at this one, but for RNs, its performance is greatly affected by the changing of order. So we can think of that. Let's recall the approximation the complexity of a Rn is considering the smoothness and decay of a memory function. But if we do a permutation of the input, the memory function is equivalent to do a permutation on the memory function. So a memory function that is exponentially decay will no longer be smooth and decay after we do a permutation. But a temporal mixing with however, if we consider the temporal mixing with an exponentially decaying filter, it will not affect the performance of Rn. However, this temporal mixing will affect the performance of the transformer. And from this experiment, we can also see that even though the transformer is not affected by the temporal mixing, the general error is larger than Rn. You can see that the Rn on this theta side is to the 10 to the -7, but the transformer, the error is greatly larger than the Rn. So we investigated that this is because transformer is generally hard to learn this kind of linear functional targets because the memory function has contained a lot of temporal ordering information in it, and transformers are generally hard to capture such informations. Okay, since I still have a little more time, I think I will also have a brief overview of the approximation rate for the temporal convolution networks. So basically, a temporal convolution network is we are applying some 1D convolution to the input sequence. Here W is the convolution filters, and at each layer we are applying some dilated convolution. So at higher layer, the dilations become larger. So this is equivalent to saying that we want to achieve a larger filter with fewer parameters by using the dilated convolution. So here K is the number of layers and M is the number of channels. And the hypothesis here can be written into this form, which is a convolution of the small filters here. And the target space, we also consider the continuous and linear causal targets, which is similar to the iron case. And the approximation here, we are to consider the approximation of the temporal convolution, we are using we want to define some regular subspace. And in this case, we are considering some tensorization techniques. So we can transform the 1D convolution filter into this tensor here. So this is basically a reshaping of the 1D filter into a tensor. And we can do the same operation to the memory function, which we can decompose using a higher order singular value decomposition. So here the approximation error is determined by some low rank approximation. And the rank here is the singular values of some geometric transformation of the memory function, which is not same as with the transformer, which is not same as the singular values we taught in the transformers. And so the informal approximation rate here says that if we assume the singular values have some certain decaying rate beta here, the approximation error using the convolution net have this rate where m is the number of channels and the beta here is the decay rate of the singular values. So finally, we can make some comparisons with transformer and Rn and Cn together. So first, we can say that transformer with relative position encoding can perform convolution. So this basically means that the hypothesis space of the TCN is contained in the transformer. So transformer is the hypothesis space we are considered here. The transformer is strictly greater than the space of the convolution networks. And let's take a look at the comparison between Rn and the convolution. So what we can say here is that both of the Rn and the convolution have strengths and limitations. So let's say we considering to learn this target here, to learn this convolutional target. So on the left-hand side, the Cn is actually can learn this one very efficiently because this one is low rank. But since this is non-smooth Rn is very hard to learn this kind of target. However, on the right-hand side, Rn is better than Cn. This one is smooth. This kind of kernel is smooth and exponentially decay. So based on the approximation result for Rn can learn this one very efficiently. But this one is of high rank. And we observe that the convolution networks with small channel size, it's very hard to learn this kind of target here. Okay, so I think to make a summary of my presentation today is that we developed the density and rate and approximation rate result for different sequential architectures. And the approximation rate result allows us to have a comparison between each architectures. And we can conclude that there is no single architecture that is good for all the targets. The performance of the model is completely determined by the intrinsic temporal structure from the target. Okay, here are some references of our work on the approximation of sequence modeling architectures. Okay, thank you.
Okay, thanks for the great talk. And are there any questions from the audience? Okay, then I have a question. Can you go back to page 17?
17, okay. This page, okay.
Yeah, okay. Can you explain again why the second term in the bracket is very small?
You mean the second term?
Yeah, because we have mh to the beta plus 1 over mff.
Yes, you are true. So basically here we say this one goes to 0, we can consider we fix image here, and if we increase the number of parameters in the feed forward part, then this term will go to 0. And actually, if we go a bit deeper, is that this one is actually an upper bound, and this one is not tight. So let's say if we increase image here, so the number of parameters will be increased in the model, but the error bound may be increased, but actually the error will not increase. So because the bound is not tight. So basically, if we look at these two terms, better we look at these two terms separately here.
I see. Okay.
Mm.
Any other questions? Okay, then I will stop recording.
Okay.